Welcome to Chapter 2, Chemistry of Life. The elements carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus are the key building blocks of the chemicals found in living things. They form carbohydrates, nucleic acids, proteins, and lipids, all of which will be defined later in this chapter. They are the fundamental molecular components of all organisms. In this chapter, we will discuss these important building blocks and learn how the unique properties of the atoms of different elements affect their interactions with other atoms to form the molecules of life. And we are starting with the building blocks of molecules. By the end of this section, you will be able to describe matter and elements in a very basic way, describe the interrelationship between protons, neutrons, and electrons, and the ways in which electrons can be donated or shared between atoms. Food provides an organism with nutrients, the matter it needs to survive. Many of these critical nutrients come in the form of biological macromolecules, or large molecules, necessary for life. These macromolecules are built from different combinations of smaller organic molecules. What specific types of biological macromolecules do living things require? How are these molecules formed? What functions do they serve? In this chapter, we will explore these questions. At its most fundamental level, life is made up of matter. Matter occupies space and has mass. All matter is composed of elements, substances that cannot be broken down or transformed chemically into other substances. Each element is made of atoms, each with a constant number of protons and unique properties. A total of 118 elements have been defined. However, only 92 occur naturally, and fewer than 30 are found in living cells. The remaining 26 elements are unstable and, therefore, do not exist for very long or are theoretical and have not yet been detected. Each element is designated by its chemical symbol, such as Hn, C, and Na for sodium, and possesses unique properties. These unique properties allow elements to combine and to bond with each other in specific ways. An atom is the smallest component of an element that retains all the chemical properties of that element. For example, one hydrogen atom has all of the properties of the element hydrogen, such as it exists as a gas at room temperature and it bonds with oxygen to create a water molecule. Hydrogen atoms cannot be broken down into anything smaller while still retaining the properties of hydrogen. If a hydrogen atom were broken down into subatomic particles, it would no longer have the properties of hydrogen. As an aside, any talk about small hydrogens in certain sectors of alternative health are completely unsupportable. At the most basic level, all organisms are made of a combination of elements. They contain atoms that combine together to form molecules. In multicellular organisms, such as animals, molecules can interact to form cells that combine to form tissues which make up organs. These combinations continue until entire multicellular organisms are formed. Pictured here is a graphic I made of a yeast cell showing the distribution of elements that make up that individual yeast cell. As you can see, carbon is the most prevalent, followed by oxygen, nitrogen, hydrogen, potassium, phosphorus, with some sulfur, magnesium, and calcium. Some more elements are involved, but these are all the major elements involved in making a yeast cell. All atoms contain protons, electrons, and neutrons. The only exception is hydrogen, which is made up of one proton and one electron. A proton is a positively charged particle that resides in the nucleus, which is the core of the atom, and has a mass of 1 and a charge of +1. An electron is a negatively charged particle that travels in the space around the nucleus. In other words, it resides outside the nucleus. It has a negligible mass and a charge of -1. Neutrons, like protons, reside in the nucleus of an atom. They have a mass of 1 and no charge. The positive, which are the protons, and the negative, which are the electrons, charges balance each other in a neutral atom which has a net 0 charge. Because protons and neutrons each have a mass of 1, the mass of an atom is equal to the number of protons and neutrons of that atom. The number of electrons does not factor into the overall mass because their mass is so small. As stated earlier, each element has its own unique properties. Each contains a different number of protons and neutrons, giving it its own atomic number and mass number. The atomic number of an element is equal to the number of protons that element contains. The mass number, or atomic mass, is the number of protons plus the number of neutrons of that element. Therefore, it is possible to determine the number of neutrons by subtracting the atomic number from the mass number. These numbers provide information about the elements and how they will react when combined. Different elements have different melting and boiling points and are in different states, or phases, liquid, solid, or gas, for the most part, at room temperature. They also combine in different ways. Some form specific types of bonds, whereas others do not. How they combine is based on the number of electrons present. Because of these characteristics, the elements are arranged into the periodic table of elements. A chart of the elements that includes the atomic number and relative atomic mass of each element. The periodic table also provides key information about the properties of elements, often indicated by color coding. The arrangement of the table also shows how the electrons in each element are organized and provides important details about how atoms will react with each other to form molecules. Isotopes are different forms of the same element that have the same number of protons but a different number of neutrons. Some elements, such as carbon, potassium, and uranium, have naturally occurring isotopes. Carbon-12 is the most common isotope of carbon, containing 6 protons and 6 neutrons. Therefore, it has a mass number of 12, which is the sum of 6 protons and 6 neutrons, and an atomic number of 6, which makes it carbon. Carbon-14 contains 6 protons and 8 neutrons. Therefore, it has a mass number of 14, 6 protons and 8 neutrons, and an atomic number of 6, meaning it is still the same element, carbon. These two alternative forms of carbon are isotopes. Some isotopes are unstable and will lose protons, other subatomic particles, or energy to form more stable elements. These are called radioactive isotopes or radioisotopes. So one application of isotopes in science is the process of carbon dating. Carbon-14 is a naturally occurring radioisotope that is created in the atmosphere by cosmic rays. This is a continuous process, so more carbon-14 is always being created. As a living organism develops, the relative level of carbon-14 in its body is equal to the concentration of carbon-14 in the atmosphere. When an organism dies, it is no longer ingesting carbon-14, so the ratio will decline. Carbon-14 decays to nitrogen-14 by a process called beta decay. It gives off energy in this slow process. After approximately 5,730 years, only 1/2 of the starting concentration of carbon-14 will have been converted to nitrogen-14. The time it takes for half the original concentration of an isotope to decay to its more stable form is called its half-life. Because the half-life of carbon-14 is long, it is used to age formerly living objects such as fossils. Using the ratio of the carbon-14 concentration found in an object to the amount of carbon-14 detected in the atmosphere, the amount of the isotope that has not yet decayed can be determined. Based on this amount, the age of the fossil can be calculated to about 50,000 years. Isotopes with longer half-lives, such as potassium-40, are used to calculate the ages of older fossils. Through the use of carbon dating, scientists can reconstruct the ecology and biogeography of organisms living within the past 50,000 years. So here is a simulation that you can find in the textbook here that will allow you to manipulate the various isotopes of a select group of elements. So for example, if we go to carbon and we have carbon-12, 6 protons, 6 neutrons, that is stable. If we add a neutron, it is carbon-13, which is also stable. But if we add one more, it becomes unstable. So we can take those back out. Carbon-12. Can we take carbons out? Take neutrons out? Yes, we can. Well, that's interesting. So nitrogen 14, if we add 1, we get nitrogen 15, which is present in the atmosphere at 0.364% and is commonly used as a stable isotope. And see, it is stable, in order to get an idea of what contribution nitrogen fixers have made to a particular organism. Now the other option here is to look at mixtures. So if we take sodium and we go with nature's mix, see that primarily almost all of the naturally occurring sodium has an atomic mass of 23. There's a very small percentage that is slightly lower. So if we go here, what if we... Okay, so if we look at nitrogen 14 versus nitrogen 15, the average atomic mass greatly favors nitrogen 14 as that's the most abundant. Looking at the nature's mix, there we go. Okay, I can't move any of that. All right, good to know. So anyway, that's that simulation. Chemical bonds. How elements interact with one another depends on how their electrons are arranged and how many openings for electrons exist at the outermost region where the electrons are present in an atom. Electrons exist at energy levels that form shells around the nucleus. The closest shell can hold up to 2 electrons. The closest shell to the nucleus is always filled first before any other shells can be filled. Hydrogen has only 1 electron. Therefore, it has only 1 spot occupied within the lowest shell. Helium has 2 electrons. Therefore, it can completely fill the lowest shell with its 2 electrons. If you look at the periodic table, you will see that hydrogen and helium are the only 2 elements in the first row. This is because they only have electrons in their first shell. Hydrogen and helium are the only 2 elements that have the lowest shell and no other shells. The second and third energy levels can hold up to 8 electrons. The 8 electrons are arranged in 4 pairs, and 1 position in each pair is filled with an electron before any pairs are completed. Looking at the periodic table, you will notice that there are 7 rows. These rows correspond to the number of shells that the elements within that row have. The elements within a particular row have increasing numbers of electrons as the columns proceed from left to right. Although each element has the same number of shells, not all of the shells are completely filled with electrons. If you look at the second row of the periodic table, you will find lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. These all have electrons that occupy only the first and second shells. Lithium has only 1 electron in its outermost shell. Beryllium has 2 electrons, boron has 3, and so on, until the entire shell is filled with 8 electrons, as is the case with neon. Not all elements have enough electrons to fill their outermost shells, but an atom is at its most stable when all of the electron positions in the outermost shell are filled. Because of these vacancies in the outermost shells, we see the formation of chemical bonds, or interactions between 2 or more of the same or different elements that result in the formation of molecules. To achieve greater stability, atoms will tend to completely fill their outer shells and will bond with other elements to accomplish this goal by sharing electrons, accepting electrons from another atom, or donating electrons to another atom. Because the outermost shells of the elements with low atomic numbers, up to calcium with atomic number 20, can hold 8 electrons, this is referred to as the octet rule. An element can donate, accept, or share electrons with other elements to fill its outer shell and satisfy the octet rule. When an atom does not contain equal numbers of protons and electrons, it is called an ion. Because the number of electrons does not equal the number of protons, each ion has a net charge. Positive ions are formed by losing electrons and are called cations. Negative ions are formed by gaining electrons and are called anions. For example, sodium only has one electron in its outermost shell. It takes less energy for sodium to donate that one electron than it does to accept 7 more electrons to fill the outer shell. If sodium loses an electron, it now has 11 protons and only 10 electrons, leaving it with an overall charge of +1. It is now called a sodium ion. The chlorine atom has 7 electrons in its outer shell. Again, it is more energy efficient for chlorine to gain 1 electron than to lose 7. Therefore, it tends to gain an electron to create an ion with 17 protons and 18 electrons, giving it a net -1 charge. It is now called a chloride ion. This movement of electrons from one element to another is referred to as electron transfer. As this figure illustrates, a sodium atom has only 1 electron in its outermost shell, whereas a chlorine atom has, there we go, right there, 1 electron in its outermost shell for sodium, and chlorine has 7 electrons in its outermost shell. A sodium atom will donate its 1 electron to empty its shell, and a chlorine atom will accept that electron to fill its shell, becoming chloride. Both ions now satisfy the octet rule and have a complete outermost shells. Because the number of electrons is no longer equal to the number of protons, each is now an ion and has a +1 for sodium, right, there we go, or -1 for the chloride net charge. Ionic bonds. There are 4 types of bonds or interactions. Ionic, there we are, covalent, hydrogen bonds, and van der Waals interactions. Ionic and covalent bonds are strong interactions that require a larger energy input to break apart. When an element donates an electron from its outer shell, as in the sodium atom example above, a positive ion is formed. The element accepting the electron is now negatively charged. Because positive and negative charges attract, these ions stay together and form an ionic bond, or a bond between ions. The elements bond together with the electron from one element staying predominantly with the other element. When sodium and chloride ions combine to produce sodium chloride, an electron from a sodium atom stays with the other 7 from the chlorine atom, and the sodium and chloride ions attract each other in a lattice of ions with a net 0 charge. Covalent bonds. Another type of strong chemical bond between 2 or more atoms is a covalent bond. These bonds form when an electron is shared between 2 elements and are the strongest and most common form of chemical bond in living organisms. Covalent bonds form between the elements that make up the biological molecules in our cells. Unlike ionic bonds, covalent bonds do not dissociate in water. The hydrogen and oxygen atoms that combine to form water molecules are bound together by covalent bonds. The electron from the hydrogen atom divides its time between the outer shell of the hydrogen atom and the incomplete outer shell of the oxygen atom. To completely fill the outer shell of an oxygen atom, 2 electrons from 2 hydrogen atoms are needed, hence the subscript 2 in H2O. The electrons are shared between atoms, dividing their time between them to fill the outer shell of each. This sharing is a lower energy state for all of the atoms involved than if they existed without their outer shells filled. There are 2 types of covalent bonds, polar and nonpolar. Nonpolar covalent bonds form between 2 atoms of the same element or between different elements that share electrons equally. For example, an oxygen atom can bond with another oxygen atom to fill their outer shells. This association is nonpolar because the electrons will be equally distributed between each oxygen atom. 2 covalent bonds form between 2 oxygen atoms because oxygen requires 2 shared electrons to fill its outermost shell. Nitrogen atoms will form 3 covalent bonds, also called a triple covalent, between 2 atoms of nitrogen because each nitrogen atom needs 3 electrons to fill its outermost shell. Another example of a nonpolar covalent bond is found in the methane molecule, pictured here right in the middle. The carbon atom has 4 electrons in its outermost shell and needs 4 more to fill it. It gets these 4 from 4 hydrogen atoms, each atom providing 1. These elements all share the electrons equally, creating 4 nonpolar covalent bonds. In a polar covalent bond, the electrons shared by the atoms spend more time closer to one nucleus than the other nucleus. Because of the unequal distribution of electrons between the different nuclei, a slight positive or a slight negative charge develops. The covalent bonds between hydrogen and oxygen atoms in water are polar covalent bonds. The shared electrons spend more time near the oxygen nucleus, giving it a small negative charge, than they spend near the hydrogen nuclei, giving these molecules a small positive charge. Hydrogen bonds. Ionic and covalent bonds are strong bonds that require considerable energy to break. However, not all bonds between elements are ionic or covalent bonds. Weaker bonds can also form. These are attractions that occur between positive and negative charges that do not require much energy to break. 2 weak bonds that occur frequently are hydrogen bonds and van der Waals interactions. These bonds give rise to the unique properties of water and the unique structure of DNA and proteins. When polar covalent bonds containing a hydrogen atom form, the hydrogen atom in that bond has a slightly positive charge. This is because the shared electron is pulled more strongly towards the other element and away from the hydrogen nucleus. Because the hydrogen atom is slightly positive, it will be attracted to neighboring negative partial charges. When this happens, a weak interaction occurs between the partial positive charge of the hydrogen atom of one molecule and the partial negative charge of the other molecule. This interaction is called a hydrogen bond. This type of bond is common. For example, the liquid nature of water is caused by the hydrogen bonds between water molecules. Hydrogen bonds give water the unique properties that sustain life. If it were not for hydrogen bonding, water would be a gas rather than a liquid at room temperature. Hydrogen bonds can form between different molecules, and they do not always have to include a water molecule. Hydrogen atoms in polar bonds within any molecule can form bonds with other adjacent molecules. For example, hydrogen bonds hold together 2 long strands of DNA to give the DNA molecule its characteristic double-stranded structure. Hydrogen bonds are also responsible for some of the 3-dimensional structure of proteins. Van der Waals interactions. Like hydrogen bonds, van der Waals interactions are weak attractions or interactions between molecules. They occur between polar, covalently bound atoms in different molecules. Some of these weak attractions are caused by temporary partial charges formed when electrons move around a nucleus. These weak interactions between molecules are important in biological systems. And that brings us to the end of section 2.1. The next video will be section 2.2, focusing on water. All right, see you later.